Welcome back to Organic Chemistry. We're going to think about oxygen-containing groups, particularly carbonyl chemistry. So we should start off, sorry, I'm just trying to get my head out of the way of that. There we go. Trying to think of carbonyl chemistry and oxygen. And this is an oxidation, stepped oxidation of an alcohol to an aldehyde to an acid. This is whatever this acid is. And depending on how strong our oxidation is and what conditions we do it in, we can sometimes stop at the aldehyde. If we have a secondary alcohol, we can't get to the acid because there's a carbon group blocking it. So we can get to the ketone, but we can't get any further. If it's a tertiary alcohol, it is hard to do anything with it in this scheme. So this is a typical oxidation reduction system. We can oxidize it and reduce it. It's very common in biochemistry because this is one of the easier groups to do a redox reaction on. So if we have an alcohol, we can oxidize it up. If we want to reduce a chemical, it will often be an aldehyde that is reduced to the alcohol or an acid that is reduced to the aldehyde. There are a whole set of chemicals used for this. If we think of this particular reaction, it used to be done with a chromium-6 reagent. Now it's much more commonly done with a manganese reagent because it's safer. But in both cases, you tend to jump straight to the alcohol. If you control the temperature very carefully, you can sometimes stop in the middle. With other weaker reagents, it's easier to stop in the middle. So if we take the industrial preparation of acetic acid, vinegar, it's done from ethanol, and that is carried out by an oxidation. The oxidation is done as double step reaction, but it is carried out straight from here to the acid. Okay, I'll stop there. So now that we've got our carbonyl group, what can we expect it to do? Well, our oxygen here has a slightly positive, Our oxygen here has a slightly negative charge on its two lone pairs that stick up in this direction, like little ears. And in this direction, out the back, this carbon has a very slight positive charge, and this oxygen has a slight negative charge, which polarizes this double bond, and that causes this carbon to be susceptible to nucleophilic attack. So if we have a nucleophile, it can come along there, and if we have an electrophile, it could, that's plus E plus, nucleophile can have a negative charge that makes it more likely, so that could come along from the top. So what can we imagine will happen with these? So if we take a nucleophilic attack, the nucleophile will attack, in this case it's a hydroxide ion, it will attack in here, in the antibonding orbital of the double bond. Unlike an SN2 reaction, this is not chiral. It doesn't have, even if these were two different R groups, I've written them the same, even if they were different R groups, the two sides are not different at the moment because of this double bond. So this is flat, it can come from either side. When it breaks out, it will form 1, 2, 3, 4, so it can form a chiral center, but it is difficult to make it attack from one side, so it will form both possible products. So let's do that, let's make that R star, so then it will form the two possible products, and the negative charge will be stuck on this oxygen. So we will make it attack our hydrogen in the second step. Let's do so this is step 1, a concerted movement of electrons, and then step 2, once it's got a negative charge on here, is to go to the hydrogen. Let me draw that. So I made a mistake in the same way, in a different way. I ended up with an achiral product because I had two OHs on it at the end. So now I've drawn it with an iodide ion attacking. The iodide ion attacks, giving us a chiral product. but it can attack from above or below, and it doesn't make any difference. So it will be usually, except in special cases, it will be usually just a mixture, an almost perfect 50% mixture of the two possibilities of the two enantiomers of this product with 4 different groups on the carbon. So with, first of all, the nucleophile attacks, the electron goes up onto the oxygen and it can hang around there for a while. Then the oxygen can attack an electrophile, and in this case it's a hydrogen, so it becomes an OH. There is, however, nothing stopping the other step happening first. So if the double bond attacks a hydrogen ion, or we can say an electrophilic proton attacks the double bond, it can get a share of the electrons, and so it can put a fully positive charge onto this carbon by taking it from here. You can't create or destroy charge, and that obviously makes this carbocation reactive in the ways that we know from before. It's flat. This was flat as well, so we haven't actually done any crimes yet, but of course this could rearrange. It's not going to rearrange very much because this OH is going to help to share the charge. The extra lone pair on this oxygen can share the charge, so it can bond back in, but it could do a rearrangement. However, the more important thing is that our nucleophile doesn't have to be so good now, because it can attack a real positive charge, whereas before it was attacking a small, slightly positively charged carbon. Now it's proper carbocation, really reactive, so this can be a nucleophile that isn't very good, like water, for example, which is a good leaving group, a rubbish attacking group. We can see more of this when we look at what happens if we put an oxygen in here. Okay, I had to move my board. So if we take something like this, which would be an ester, and we attack it with water, that's what we want to attack it with, we discover that it can proceed better under acid or basic conditions, and it doesn't matter which. Under acid conditions, first of all, we protonate this oxygen, and under basic conditions, our nucleophile is a hydroxide ion. Forgot to draw a bond. So the hydroxide ion can attack here. Hydroxide ion is not very common in acid, so there's not going to be a lot of it there. So we need water to attack, and it's going to do it by making this carbon positive. So let's draw the next step. Okay, so we get to this step, and our water is going to attack this species, which is the carbocation. It's the same as we had before, just there's an OR on here, so something else is going to happen later. And in this case, we've got this weird square molecule where it's got 3 oxygens on 1 carbon and a negative charge, and it's obviously really unhappy. It's in basic conditions, so it can't pick up a proton very easily, but it can kick back in. So in this case, let's draw this one. So this is going to be up to here. It was positive, so this is positive. So this can lose a proton. Let's take that off to get to the same place. Just this one is neutral and this one is charged. In this case, we're going to pop our electron back in, our electron pair back in, and this carbon then becomes very unhappy. So it's got to lose something. Either this hydroxide group can fall off, but that goes back to where we were, or this group could fall off. So let's do that one so that we get to a different product. In this case, we have much the same, but in this case, one of these 2 hydroxide ions, or hydroxide groups, one of the 2 alcohol groups, can lose a proton. So we need to take it away with a base somehow, typically water, because we're in acidic conditions, so the best we can do is water. So that would be our water. taking a proton away from the alcohol, allowing it to fall back off, and let's do the same reaction as before. That makes our product more stable. We get the same product as here. It's just here we have a proton transfer in this step, and here we're using a negative charge, which gives off a negatively charged ion. Here we're going to give off a negatively charged ion, and then it's got to get the proton off from either another one or back off this water. So this is the product in both cases, that we have an acid group and an alcohol. It's an de-esterification effectively. We're breaking the ester, and we can attack it with water in this case, or we can attack it with a base and we get the same product, but we use an acid or a base catalyst, in that direction. But what we know about catalysts is they typically work in both directions, so we would expect the same thing to happen in the other direction, which you can easily imagine. So if we swap this R for an H and the OH for OR, then the reaction works exactly the same. It just makes the ester, which is this point, the one that doesn't have a lens flare, it's this one, instead of the alcohol and the acid. So we can go in both directions. It's an absolutely typical catalyst. It increases the rate of reaction to the acid or the base, increase the rate of the reaction, but don't change the weighting of the starting material and the products. This type of reaction, esterification, typically has unusual kinetics in that the equilibrium is very close to 1, that you usually get products and educts in the same reaction, and so to make it go the way that you want it to go, you usually do something. So either we would add a lot of water to make it go that way, or we would remove the water by adding an acid or a base that sequesters water to make it go in this direction. Otherwise, we typically end up with a terrible mixture with far too much of the starting material and not enough of the finishing material. If we switch our water for a different alcohol, so in this case we've got R-OH, and I've used the acid catalyzed route, but it works in both directions. If we take a different alcohol, it can do the same thing, and then we get to the same step that we had on the other reaction, that we can lose either of the two groups. So now we are forced, really, if we want to choose our product, we are forced to put in a lot of this alcohol compared to this ester if we want this ester as our product. Why would we do that? Let me draw that first. I think it's going to be easier. So this would be something like a natural plant oil. It has a glycerol, which is propane triol, propane 1,2,3-triol, which is esterified, so it behaves as the alcohol. It's esterified to 3 acids. They're not usually the same acid in every case. And I've drawn in this case some double bonds in there. The natural double bonds are the cis double bonds with the 2 groups on the same side. Those are the good ones. Trans double bonds are the baddies. So we either have saturated carbon chains or unsaturated carbon chains, and the natural ones are usually cis double bonds. This is plant oil, and as you know from plant oil, so if we try to burn olive oil, for example, it's not great. It doesn't burn very easily, and that's mostly the fault of this group and the fault of it not being very easy to vaporize. It's very difficult to evaporate this, and once we start to evaporate it, it starts to char anyway, and then bad things happen. What we would like to do is evaporate our fuel and it burn in the gas phase. That's what we normally do for burning fuels for driving our car or whatever. So if we want to convert this into diesel fuel, Or, for food science, if we want to measure this molecule here, we want to know whether this really is a cis unsaturated fat and where the double bond is. We want to know how many of them we have compared to the other things in olive oil to characterize it, or we want to know whether the seller is cheating us and giving us a different type of oil. If we can get these 3 fatty acids off and measure them in a gas phase chromatography measurement, we will be able to tell that. But we need to get there first. So we need to do this transesterification. So we need to convert this ester into a different ester because fatty acids, carboxylic acids, are not very good at evaporating. They're quite solid. Big ones are solid. But if we have an ester, it behaves like a non-polar molecule. An ester is very much like oil. And that's good because it means we can evaporate it comparatively easily. But what we need is to break these linkages. We need 1 cap for each one. And the solution is to take the methyl ester. So to take methanol, so we want to do plus methanol, MEOH, like that, plus catalyst. And we can use an acid or a base catalyst. Very often we use a base catalyst in this case for doing it at home. Very often it's a boron catalyst if you do it for analysis. Then we do the same transesterification. So let's use a base catalyst, OH minus. So the first step is step 1. OH loses it. Now let's draw bond to my hydrogen. It loses its. So we got our base B minus, and it steals that proton off here. Goes to the methanoate anion. The methanoate anion is now going to go and attack our fatty acids. So let's just do this one on the right because it's the easiest and I don't have to cross over anything. So my methanoate anion is going to attack onto this delta plus, sorry. It's difficult to draw a delta plus in small with a fat board marker. So that is going to attack in there. It's going to knock my electrons out of the double bond onto the oxygen. And that gives me, so all of the other rest of the molecule, O, bang, O minus, and O, Me there. So that would be my intermediate, and I am hoping that most of the time it kicks in here and makes the anion of the glycerol, and then I can get my fatty acid off. Once it's off, it is got a lower boiling point, so I can boil this off, so I can extract it so that it doesn't form back to the starting material, because there's nothing stopping it doing that. The catalyst works well in both directions, so I need to make sure that it doesn't go anywhere else. And in this case, I don't want any water to be in there, because if there was water in there, it would compete with my methanoate anion. It would also react with it. So in this case, we would like it to be super dry. So if you make diesel at home, biodiesel at home, don't do that. It's probably rather dubious anyway. The laws on it are very odd. But the process is we take our cooking oil, our cheap oil. Obviously it's no good unless it's cheaper. So we get our cheap oil, we get some methanol. Ethanol works, but not as well. We get our methanol, we attack it in strongly basic conditions, and it's dry, so we don't get the acid. And then we extract this. So our product is actually this thing. Like that is the methyl ester of our fatty acid, and this technique is called fatty acid methyl ester, or FAME, and is used for making it fly, making it go into the gas phase so that we can measure these chains. So one industrial use of this reaction. The reason that this reaction is important, and the reason that I've spent one whole time talking about it, is not that it's complicated. It's actually comparatively simple, but it is a general reaction. And it is super important because we have formed a new carbon-carbon bond. So obviously in this case we're forming an oxygen carbon bond, but if we have a nucleophile that is a carbon, we can form a new carbon-carbon bond, and so that is critical for making carbon chains. If we need to make our carbon chain longer, this is one of the very few ways that we can do it. It's quite difficult to do. In nature, it's how these fatty acids are formed. They are formed by adding carbon in a very similar reaction. It's related to these reactions. If we make polyester, polyester is a polymer of a diacid and a dialcohol, and it forms a long chain of these bonds. So polyester, not this polyester, but polyester of clothing would be the same thing, fleece material, but it's too hot for me to be wearing a fleece now, so I've not got one. So fleece material is polyester, and it is typically a polymer of a diacid and a dialcohol, and it's polymerized in this way. If you get acid on your clothes, it makes a hole in it. You will, you probably haven't experienced that, but you would have if you'd come to lab. When you come to lab, you will discover that you get a little bit of acid, a splash of acid on your clothes, nothing happens. Cotton is also a polyester material. It's a natural polyester between cellulose molecules, and that also degrades in the same way. So once there's acid on there, it catalyzes the hydrolysis of the ester, and when you wash it the next time, nothing happens when you get the acid on, but when you wash it the next time, you get a hole. A hole appears as if by magic in your clothes. It does it on cotton, it does it on polyester, and it does it on proteins as well. So if we take wool, wool is a protein, it's hair from a sheep, obviously, usually, or maybe a rabbit. If you're rich and you've got Angora, then it's not Angora, it's the other thing. If you got clothing made out of natural animal hair, it's a protein, and the protein bond is an amide bond, which is this thing, NR2. So this bond is identical to an ester bond in that if we have a nucleophile, it can be cleaved in the same way. So proteins can be hydrolytically cleaved in exactly the same way that cotton can, in exactly the same way that polyester can. The chemistry mechanism is very, very similar, and it's the key to it is this oxygen polarizing the carbon, and the fact that unusually for carbon it can hang around for a little while in this state, for example.